Does anyone have any questions or anything while we're waiting to start? Okay, so it's time to begin. So I will. Okay, can everyone see my screen and hear my voice?
Yep, we can.
Okay, great, thank you. Yeah, okay, so we got as far as this, and today we're going to talk about this Quinone redox flow battery at near neutral pH with a record capacity retention rate. This is from the Aziz group at Harvard again. So let's find out what's going on here. So they found this particular molecule. I don't know what its name would be. So we won't bother trying to pronounce it. But you can see it's a very large molecule. It's a quinone. It has the quinone groups here. So it can attach a hydrogen at each of these points and act as a molecule in a redox flow battery. So here they're just showing the cyclic voltammograms of this material during reduction and oxidation in various pH solutions. And they're just really showing the reversibility of the thing. Okay, so this is going to be the negative, the molecule they use as the negative in the flow battery. And the reversible reaction going on is very simple. This thing just reacts with water and an electron to make the hydroquinone and OH, and this is reversible. Just like the other quinone reactions we've seen in the last few days. So they talk about what the catholyte and the negolyte are like. So they dissolve 0.5 molar of this salt in the negolyte, and they're using potassium ferricyanide in the pozolyte. Okay, so half a molar of this thing and 0.4 molar of this and 0.1 molar of that, all dissolved in aqueous solution. So how does this thing actually work? So we draw our typical flow cell schematics. So on the positive side, you've got these potassium ferricyanide species around. And when you pull electrons out of the positive current collector during the charge of the cell, this anion gets oxidized to this anion. So the iron 2 goes to iron 3. And the electron comes along over here, and the quinone gets reduced to the hydroquinone. Now, if you look back, you learn that this thing is in a pH 9 solution. So there's not very much OH around, and there's not very much H plus around at pH 9. But there's a very high concentration of potassium in solution, half molar in potassium. So the species that crosses the membrane to maintain charge neutrality is potassium. The potassium moves from right to left during charge of the cell. So if you look at this, you'll realize that during charge, the negative electrolyte solution gets more rich in pH and OH, so the pH should increase. So as the cell is charged, the OH content increases over here in the negative side, and the pH should increase if this reaction is what's going on. If H plus were crossing, but mind you, there's virtually no H plus at pH 9. If H plus were crossing, then the pH would not increase. So you can get some feel for the validity of this reaction by monitoring the pH of the negative side solution during charge and discharge. Okay, so any questions about this?
Yeah, Jeff. So I noticed on the previous slide that they had a little bit of K4 ferricyanide and then a little bit of K3. Is that just to make sure the posilite is in the right state of charge, like kind of equivalent to the anode side?
Probably it's to get the iron in the right overall oxidation state.
Okay, thanks.
Okay, so let's see what happens when this cell operates. Yeah, so like I say, the pH should change as the cell operates. So here's a cell that's charging and discharging again and again and again. And down below, they're measuring the pH on the negative side. And it's really hard to tell because it's so compacted, you know, whether the pH is increasing during charge and decreasing during discharge. So I just zoomed in on a piece of it and then stretched it out in the horizontal sense. And sure enough, the pH increases when the cell is charged, and the cell is discharged and the pH goes back down. So that's pretty cool, I think. And it looks really repeatable over these 48 cycles. It doesn't look like there's much impedance buildup happening, and the pH changes are very repeatable. Now, mind you, this isn't taking very long. That's half an hour, right? So they're really cycling this thing like crazy. And then they show you the capacity versus cycle count. So discharge capacity is this downward facing triangle. Here it is. And charge capacity is the upward facing triangle. There it is. It's a little bit bigger than the charge capacity. So the Coulombic efficiency, like many papers published in high impact journals, is plotted on a ridiculous and stupid scale from 0 to 100%. So you can't tell that the Coulombic efficiency would be, you know, somewhat different than 100%. And then they also show you the energy efficiency, which, you know, like many flow batteries, is somewhere around 65%. Now, I don't know what would happen in this case if they operated at a lower C rate. You know, it's a very high C rate. They have 450 cycles in just 12 days. But you can notice that the energy efficiency is slowly going down. It's a downward slope here. And that will be because the voltage during discharge is going down and the voltage during charge is going up. You can see this happening, right? You can see that cycle 480 is above cycle 1, and cycle 480 is on discharge is below cycle 1. So there's an impedance buildup in this cell. And this is a lot of what Charlotte Clegg is working on in her graduate studies here at Dow, is trying to understand how the impedance in these flow batteries changes with time due to buildup of reaction products on the carbon fiber paper, on the positive side and the negative side, using XPS and other tools, impedance spectroscopy, for example. Oh yeah, so they don't even mention this impedance growth in the paper at all, not once anywhere in the paper. Any questions about this? Okay, so then they go on and make some projections for lifetime. So they say 97% of theoretical capacity was cycled for 480 cycles, 12.3 days to complete. The average capacity retention rate over the 480 cycles was 99.99964% per cycle at an average coulomic efficiency greater than 99.9%. A fade rate of 0.00036 per cycle, or 0.014% per day. So then they go on down and say that the 0.014% per day would be 5% per year. Okay. But they don't tell you what's going to happen with respect to this impedance growth, and it's very tough to do that, as you all know, in just 12 days of testing at room temperature as well. So then in the supplemental information of the paper, they tell you about the volumetric capacity and the energy density of this thing. So they talk about, what the solubilities are and the theoretical volumetric capacity, blah, blah. So using established methods of raising ferricyanide solubility, the energy density would be 20 watt-hours per liter. That's the theoretical volumetric energy density. The demonstrated volumetric energy density is 7.7 watt-hours per liter. So you can compare 20 watt-hours per liter to a lithium-ion cell nowadays. A good one for an energy cell would be 800 watt-hours per liter. And a very long lifetime cell would be 600 watt-hours per liter. And this is the thing about flow batteries, is that the energy densities are low, but you can make very massive tanks and store a lot of energy out in the tanks. Someone was going to ask a question.
Yeah, so I was going to ask about how they what's included in the energy density calculation. Do they include like the footprint of the pumps or
No.
anything like that?
No, this is just based on the solutions.
Okay.
Hey, Jeff?
Yeah.
I was surprised to see that, they're estimating 5% capacity loss a year, but they were saying that this is like the best capacity retention reported for flow cells. So for all of those examples you showed a few lectures back.
Organic aqueous. Best capacity retention for organic aqueous.
Okay. Okay, so not the best for fuel cells. Okay. So do you know if this similar system has been deployed in grid storage applications at all, or is it mostly just aqueous flow cells?
The only thing employed in big so far is vanadium.
Okay.
Yeah, these things all have problems with stability of the organic molecules in either the oxidized or reduced states. And when the temperature goes up, those stabilities become much worse, just as we know, right? All these decomposition reactions accelerate dramatically with temperature. Okay, so I want to spend some time now talking about what's the best kind of a flow battery to use. Okay, so the thing is, we have to try to make some kind of a hand-waving Feynman style consideration of a flow battery. So we're going to do a Feynman style estimate for the cost of a flow battery. And what we're going to do is we're going to assume that the reactor costs nothing. The pumps and the reactor, they're given to us for free. And all we're going to care about is the cost of the chemicals. I'm going to try to figure out, what the cost per kilowatt hour is for a flow cell. Anyone that works in my group knows that we get harped on all the time by our industrial partner. We really have to keep an eye on the cost per kilowatt hour of anything that we bring to the table. It has to be as low as possible. So we're going to assume that the active species costs X dollars a kilogram. So that would be, any of these organic molecules or vanadium. The vanadium species, X dollars a kilogram. And the molar weight of the active species is M sub A for active. Okay, and we're going to talk about, the units will be kilograms per mole. And we're going to assume that the cost of the electrolyte is Y dollars per kilogram. Okay, and we're going to assume that the solubility of the active species in the solvent is S kilograms per kilogram of electrolyte. So S kilograms of our species in kilogram of electrolyte. And we're going to assume the voltage is V, and we'll assume a 1 electron redox process in the active species. And if it turns out to be 2 electron redox species, we just get double the kilowatt hours per kilogram. Okay, so we have to remember what these things are, and I'll keep reminding you as we go along in this little exercise. Okay, so what is the energy available in 1 mole of redox species? So we have 1 mole in the catholyte and 1 mole in the anolyte. Okay, so we've got a mole of catholyte and a mole of anolyte. Well, it's going to be the voltage times Faraday's number, because Faraday's number gives you the charge per mole. Right? There's 1 electron transferred from the catholyte through the external wire to the anolyte side. So it's V times F. Let's convert this to kilowatt hours per mole. Okay, well, 96,500 coulombs per mole, you have to convert that into amp hours, and you get the voltage of the cell times 26.8 watt hours per mole. So if you want this in kilowatt hours, it's 0.268 times V. So if the voltage of the cell is 1, it would be 0.0268 kilowatt hours per mole of the species. Okay. Then you need to figure out how much of this catholyte you need. Well, you need 1 mole of it, and you know the molar weight is M sub A. And then you need the fluid that it's dissolved in, and that's M sub A divided by the solubility. So let's just go back for a minute. So let's just say you could get 0.1 kilograms of the active species into 1 kilogram of electrolyte. So that would mean S is 0.1. So if S was 0.1, that would mean you would need 10 kilograms of the, 10 kilograms of the electrolyte plus your kilogram of, if S is 0.1 and you want to have, you need 10 times the mass of the electrolyte compared to the species if S is 0.1. And then you need the cost. The cost, well, we assume that the active species costs X dollars per kilogram, and we assume the electrolyte costs Y dollars per kilogram. So that's the cost of the catholyte for 1 mole. 1 mole of catholyte costs this much. And we'll assume the analyte is exactly the same, just to keep things simple. It might cost more and it might cost less. So the chemical cost per mole is twice this thing here. There it is. So then the cost per kilowatt hour is twice this cost per mole times the divided by the number of kilowatt hours you get per mole. That gives you the cost per kilowatt hour. This is dollars per mole, and down in the bottom is kilowatt hours per mole. So when you divide them, you get dollars per kilowatt hour. So there you go. So this is something we can explore this formula graphically if we make some reasonable assumptions for the solubilities and the masses, the molar weights of the various chemicals. And also for the unit costs per kilogram of these two things. So one of the things you should bear in mind is that these organic species, like AQDS, this was anthraquinone disulfonate, has a pretty big molar weight, 368 grams per mole. And this thing from the world best organic flow cell has a molar weight of 630 grams per mole, so it's a lot. And remember, they were running this in the solution at only 0.5 molar, right? So it was a very dilute solution. So let's see what happens here. The first thing we need to do is sort of figure out what some sort of costs are. So here they're talking about in the vanadium redox flow battery, you know, the cost in 2014 for the vanadium would have been about 29 per kilo. And then they make some estimates here that in the future, if there's a lot of vanadium being used, the cost might be $7 a kilogram. But maybe there'll be a shortage of vanadium and the cost would be $37 a kilogram. So there's some estimates for the cost of vanadium based on a lower prediction and an upper prediction. So we'll take $20 a kilogram for vanadium, just say. And in the vanadium redox flow battery, the positive costs the same amount because they're both vanadium. And you use a very simple electrolyte of sulfuric acid and water, which costs about 10 cents a kilogram. If you use an aqueous redox flow battery with organic molecules, you know, the chemistry is to be determined. What will the chemical cost? They say $5 a kilogram, average $5 a kilogram. And if it's aqueous, again, the electrolyte doesn't cost much at all. But if you're going to use a non-aqueous redox flow battery, again, the chemicals are like $5 a kilogram in the deep future. And the electrolyte, assuming it's a non-aqueous solvent that's not so weird, would be between $3 and $7 a kilogram. So use 5. So these are sort of numbers that are projected in the future, and we'll see what happens when we put them into our little Feynman model. Okay, so here's the graph, right? And we're going to talk through this thing very, very carefully because it's really the bottom line. So let's start in the lower panel. What we're plotting is the dollars per kilowatt hour for the chemicals used in the redox flow battery with an aqueous electrolyte and assuming 1.5 volt operation, which is generous because normally they're more like 1 volt, but we'll say 1.5 volt. We're assuming that the electrolyte cost per kilogram, which is Y, is 10 cents a kilogram, just like on this slide. And we're assuming that the molar weight of the species that's being, the active species is 100 grams per mole. So 100 grams per mole for an organic redox species is incredibly small. Think about benzene as an example. Benzene is 78 grams per mole. So as soon as you start talking about any kind of anthraquinone, you've got 3 benzene rings and some other stuff hanging on there, you're way over 100 grams per mole, more like 300 grams per mole over here. And then this is the solubility. So can you get 1/10 of a mole, 1/10 of a kilogram of your stuff dissolved in a kilogram of water, for example, or 2/10 dissolved in a kilogram of water, 2/10 of a mole dissolved in a kilogram of water. And then you can look at the graph. So if your active chemicals cost only $5 a kilogram, then you're around $30 a kilowatt hour if the molecules are 100 grams per mole. But if they're 300 grams per mole, already you're jumping over $80 a kilowatt hour. Okay. So this means if you're measuring costs of chemicals per kilogram, you have to have low molar weight species to have a low cost. By the time you're up at $80 a kilowatt hour, you're more than lithium ion. And this is just the cost of the chemicals here. And once the chemicals start costing more, you're just doomed. So you cannot use costly chemicals at all. Now, if you go to the non-aqueous system, things are even more dramatic because now the solvent costs $5 a kilogram. It's not water anymore. And now the curves, are very, very different depending on the solubility because you need way more solvent. So if you use a molecule that can be only dissolved at 100 grams per kilogram, then even if the active chemicals cost nothing, the solvent cost will kill you. And you have to have a solubility of the order of 500 grams per kilogram of solvent to get the costs to come down. Okay, And this is for, again, for a active species that's only 100 grams per mole. If it's 300 grams per mole, the slopes just go up like they do over here. So the point of this is, when you're working in these systems, you have to notice the incredible importance of solubility for non-aqueous systems. Okay? It's less costly electrolyte when the active chemical is highly soluble. And many of the molecules that people propose for non-aqueous redox flow batteries are not soluble to the level of this blue or pink or purple line here. They're more like the black line. And for aqueous systems, solubility doesn't matter because water doesn't cost anything. You just have to have a bigger tank. But we're not worried about the tank costs here, just the chemical costs. And this is because the electrolyte is free, but if you look carefully, the molar weight is a killer here. And when you go back, you look at the world's best flow battery at the time, it was 0.63 kilograms per mole. You get 2 electrons, so that's like 330 grams, 315 grams per mole. That means you're on this line. So even if you can buy this stuff at $5 a kilogram, you're still too expensive to even think about. So the point of this little exercise is, with virtually no brain, you can convince yourself if what you're working on has any chance of being useful or not. And you should guide your research in a way that you're working on something that's useful and something that, as opposed to something that's completely not useful. Okay, so are there any questions about this diagram and how we got here? I mean, it's hard to see how these equations work, but they're very simple. So if I give you a homework to play around with this stuff, you'll be able to figure it all out. If you go to vanadium, we didn't talk about vanadium, right? Well, you go back to vanadium here. Vanadium's 20, okay, 20. Go to 20 in an aqueous, doesn't matter what the solubility is, there you are. Chemical cost is $100 a kilowatt hour. Can't beat lithium ion. This is without tanks, without pumps, nothing. If you use the lower limit at $7 a kilowatt hour, then you're here, you're about 40. $7 a kilogram gets you about $40 for the vanadium chemicals that you need.
Jeff, is there any comparison of the cost with respect to the lifetime of these batteries? I mean, I think this is the initial cost which we are investing, but how about the whole lifetime in comparison to that?
Yeah, again, you would, you would have to say, what is the lifetime of these things? And if you believe the manufacturers where they have a 25-year lifetime, and maybe more, that's pretty decent, right?
Yeah.
And you would do the same type of calculation for lithium ion. You would say, what's the lifetime of your lithium ion system, and compare the two. We talked the other day about whether these vanadium systems need to have maintenance, where somebody's going in and having to readjust the balance between the positive and negative from time to time due to hydrogen evolution or whatever. You know, I just don't know. It's interesting, just a little story here. Around 2001, I guess, maybe 2002, we got involved in fuel cell research with 3M. And the main reason I was interested in doing that is because I didn't know where the ghosts in the closets in fuel cells were. You know, fuel cells look great. Put in hydrogen, you put in oxygen, you get water and electricity. They work like a charm, and there's no problem. And the question was, you know, will they be a better alternative for the world than the lithium-ion battery, or transportation and whatever? So it was important to get involved and figure stuff out. And at the end of 10 years, I was pretty confident that I knew where the ghosts in the closets were. And I think it's the same thing with these aqueous, like a vanadium redox flow battery. You really need to work on it, get heavily involved to know where the ghosts in the closets are. And then you could say, okay, you just leave it for 25 years, you don't have to touch it. It works like a charm. You don't have to rebalance anything, and that's what you want. But I don't know if that's true or not.
So Jeff?
Yeah.
Even if you have to, you know, rebalance your battery from time to time, if you already, you know, have the infrastructure in place, and it's just a matter of, say, you know, replacing one tank with a fresh tank, wouldn't that give you, I guess, more bang for your buck compared to a lithium-ion cell that reaches the end of its lifetime after some decades, and then you just have to swap the whole system for a fresh battery, maybe? Or is that not
Well, it's
true?
hard to say. You know, what happens to the reactor in the redox flow battery? You know, do they build up impedance over time? They certainly do in the non-aqueous case. In the vanadium redox flow battery, I don't know what impedance as a function of time looks like in those things. So, you know, if you don't have to change the reactor, and all you have to do is, let's just say, replace the chemicals, well, you can see that replacing the chemicals is not cheap, right? It's not a cheap thing at all. So at some point, you sort of wonder, you know, what's best. So I'm not saying redox flow batteries are a waste of time. I'm just saying you have to think carefully about what you're doing. Don't work on a system that has a very high molar weight and a very low solubility if you're going non-aqueous, because that would be not very smart. Okay, so let's see where we're going now. Oh yeah. So this is this chart is from a paper. It's this paper, I think. But it compares, you know, the prices for different types of energy storage systems. So lead acid, lithium ion, vanadium redox flow, aqueous redox flow, non-aqueous redox flow, zinc bromine. This is a polymer lithium sulfur battery, and this is a non-aqueous redox flow hybrid system. And this is fairly dated, right? But at this point, the vanadium redox flow was around $150 a kilowatt hour. Lithium ion they had pegged at around 225. Well, lithium ion today is 100, and people say it's going to go into the 60s or so. And we learned that just the chemicals for the vanadium redox flow, depending on the vanadium price, could be as much as 80 just for the vanadium. And in the best case, it could be 40 without pumps, without tanks, without anything else, So these numbers are, who knows what the truth is for vanadium redox flow. Maybe the people doing it know, but I don't know. Okay, so the point is that costs for lithium ion have come down a lot. It's unclear what has happened to the cost of vanadium redox flow. One would have thought that the cost of vanadium chemicals was fairly well known when this chart was made. And I don't know if you can believe these other redox flow numbers. What will the lifetimes be? That's another question, like Divya asked.
Hi, Jeff.
Yeah.
So I'm just trying to talk about this the pollution, the environmental issues related to the three batteries. Looks like the lead acid and the lithium ion and the Vanetics the VRFB, they are best in terms of the cost. But you mentioned before, like the lead itself, the vanadium itself is toxic, right? Can we say that out of the three systems, the lithium ions cause the least amount of pollution? Because the lead acid itself also causes pollution because of lead.
Well, the lead acid has a very, very good recycling infrastructure in place at the moment. So 99% or something, between 97 and 99% of lead acid are recycled and used again. Lithium ion is coming that way. Actually, somebody sent me a link to a discussion with J.B. Strovell about redwood materials and where they are at the moment. I'm going to forward it to you all because that's a lithium ion recycling company. And vanadium redox flow, I think you could certainly recover the vanadium chemicals in this situation and use them again. I would say of all these things, I would say lithium ion is probably the most difficult to recycle because you have to get all the various components out, and the positive electrode is pretty much going to be reduced back down to the elements, and you have to make new positive electrode from it. The construction of a lead acid battery is the simplest. You can just take out the lead plates and recover the lead pretty easily. So that's another consideration. Okay, so this is a wonderful paper. It really talks about how to get to low-cost storage using aqueous or non-aqueous flow batteries. I'll give you a homework problem associated with this paper. I'm not going to talk about it here today because I think it's better for you to look at it in the homework. It really does a better job than my little hand-waving approach here. And the conclusions at the end are the same. You have to have high solubility, you have to have low-cost chemicals, and basically the same conclusions come out. They just do a better job, more professional. Yeah, one of the things that they say here, reduces unneeded molecular complexity of known redox structures to minimize equivalent weight, can reduce costs and may lead to increased charge carrier concentration. So the idea is you have to have small molar weight materials to lower costs. Design space for non-aqueous appears to be broader than that of aqueous systems. However, constraints for non-aqueous systems of active material solubility and electrolyte costs create additional hurdles that must be overcome. And so that's exactly the conclusion that I reached, right? You have to have high solubility and you have to have low molar weight. And the solvent has to be cheap too. You can't have a expensive electrolyte. So they reached the same conclusions that I did in their work. Yeah, so there's dozens and dozens of flow batteries out there. The review paper by Skilla Kazakos. I'll give you a homework problem on that also, where you can take a look at it and say, oh my God, there's a gazillion types of flow batteries out there. And, you know, they're kind of being weeded out now over time. And really the vanadium redox flow battery is the only one that's being pushed forward at a big way into commercialization at this moment. Some people promote systems like this, where you have a sort of hybrid. So what's happening here is, in one side, you make bromine goes from bromine ion to bromine gas, and on the other side, you're plating and stripping zinc. Okay, so you have a zinc metal electrode that's being stripped and plated. So it can be a fairly complicated set of things. And I think this is discussed in the Skilla Kazakos paper also. So there's all kinds of strange things that are being proposed and worked on. Okay, so that's all I want to do on flow batteries. Just to give you a flavor for how they work. And I think you'll learn a lot more from the homework than you will from me. I think that's the way it goes with most of the homeworks. So if there's any questions, I can try to answer them.
Do you know if the zinc system also has dendrite problems there? Because I've heard zinc can also deposit as dendrites.
Ron, I would say it would be a miracle if the zinc system doesn't have a problem with dendrites. You know, let's talk about zinc dendrites for a minute, okay? So we have a company in Dartmouth called Salient, and they make rechargeable zinc manganese dioxide cells, and they use a zinc metal negative, okay? And you know, one of the goals is to, like we do in half cells here with lithium metal, to charge and discharge, you're stripping and plating the lithium, or with anode 3, you're stripping and plating the lithium, and you don't want dendrites and you don't want poor coulombic efficiency. With a lithium metal cell, you know, to get 1,000 cycles, even with the best electrolyte, with the best liquid electrolyte, you would need like a 6 or 7-fold excess of lithium. And you would have to hope that while you're cycling, the dead lithium doesn't create dendrites that short your separator. And we know you can't use a thick separator, or you, from our work in the cell spreadsheet model part of this course, you can't put a thick separator in, or your energy densities just go to hell. So these guys that are doing rechargeable zinc, you know, they have to worry about dendrite penetration. Their separators are over 100 microns, you know, and they have a situation where they use up to 10-fold excess of zinc to get the kind of cycle life that they need. So when you think about the added cost of the extra zinc, the impact on the energy density, you know, you really start to wonder. So you're absolutely right, Ron. Dendrites are important. Okay, this is a good time to stop, I think. We'll stop a little early. Everybody can have 3 minutes of rest or something. Yeah, I'll send you the notes for the fuel cell part, which will start on next week.